Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the upcoming test. So it's all about rational and irrational numbers, but in order to understand this, we need to have a good understanding of the link between fractions and decimals. So let's start by converting each of these fractions to decimals. So for 7 over 40, we're saying how many times does 40 go into 7? So just put a few zeros here. It doesn't matter if you write the wrong number of zeros. So 40 into 7 goes 0 times remainder 7. 0 times 40 is 0. You need 7 more to get to 7. So decimal point goes above decimal point. So now we go, how many times does 40 go into 70? Well, it goes once, remainder 30. Now we're saying, how many times does 40 go into 300? Well, 4 goes into 30 7 times, so 40 goes into 300 7 times, and the remainder will be 20. 7 times 40 is 280, remainder 20. So then 40 goes into 200 5 times. There's no remainder, so I stop there. All right, let's do 1 over 27. We're saying how many times does 27 go into 1? So once again, write a few zeros. Doesn't matter if you get the wrong number of zeros. So 27 goes into 1 0 times, remainder 1. Decimal point goes above decimal point. Now we go 27 into 10. Well, that goes 0 times, remainder 10. How many times does 27 go into 100? Well, 3 times 27 is 81, remainder 19. So how many times does 27 go into 190? Well, 7 times 27 is 189, and there's 1 left over. How many times does 27 go into 10? 0, remainder 10. How many times does 27 go into 100? 3, remainder 19. How many times does 27 go into 190? It's 7, remainder 1. Hopefully now we can see that there's a pattern. We're just going to see this go on and on forever. So 1 over 27 is 0.037037037037037. This is what we call a recurring decimal. It's decimal expansion. The numbers after the decimal point go on and on forever, and there is a pattern. This ... means goes on forever. It indicates a recurring decimal. So to write this in exact form, we write 0.037. We include the numbers that are repeating, and we just put dots or a dash over those numbers that are repeating. So this is the exact form of the decimal for that. So why is it that 1 over 27 yielded a recurring decimal, yet 7 over 40 yielded what's called a terminating decimal? Terminating meaning ending. This one didn't go on forever. So why is that? Let's have a look. So it turns out if you have a simplified fraction a over b, it will yield a terminating decimal if and only if b equals 2 to the n times 5 to the m. What does that mean? Well, that means your fraction needs to be simplified. Its decimal will be terminating if the only prime factors of the denominator are 2 and 5. It has no prime factors other than 2 or 5. If b, the denominator of a simplified fraction, has any prime factor other than 2 or 5, it will yield a recurring decimal. So for example, for 1 over 500, I know that that's going to be terminating. Why is that? Well, 1 over 500 is simplified, obviously, but 500 you can write as 5 to the power of 3 times 2 squared. It is 125 times 4. The only prime factors of 500 are 5 and 2. So this will have a terminating decimal. Now, it turns out that you take the larger of these powers, the larger of n and m, and that tells you how many digits before it terminates. So 1 over 500 will have 3 digits before it terminates. So 1 over 500 is equal to 0.002. 3 digits before it terminates. It's terminating because it stops. Now, on the other hand, 1 over 600 will have a recurring decimal. So why is that? Because its denominator, 600, has a factor prime factor other than 2 or 5. It's divisible by 3. Turns out 1 over 600 is equal to 0.0016 recurring. That's what it is in exact form. So when we write it like this, it's only the 6 that is repeating. Its decimal is 0.00166666666, and so on. Only numbers with a dot or dash above them are repeated. 1 over 111. Well, 111 is divisible by 3. It doesn't have 2 or 3 as a prime factor, so it will yield a recurring decimal. We can tell that without using our calculator. So it turns out 1 over 111 is 0.009 recurring. So 0.009, 009, 009, and so on forever. Now don't worry, I wouldn't ask you to do 1 over 600 or 1 over 111. I wouldn't ask you to convert them to a decimal without a calculator. But I just wanted to make the point. We actually kind of get 2 types of recurring decimals. For this one, we sort of have a terminating part, then a recurring part. Here, we have just the recurring part. So why did these yield different types of recurring decimals? We won't be tested on this, but just for interest, it's because 600 does have factors of 2 or 5. It also has a factor of 3. That's why it's recurring. But because it also has factors of 2 and 5, we get a decimal that has a terminating and recurring part. On the other hand, 111 is neither divisible by 2 nor divisible by 5. And that's why we only got a recurring part after the decimal. Now, I really need to make this point. The fraction a over b has to be simplified. Let's look at 17 over 34. Well, clearly, 34 has prime factors other than 2 or 5. It's divisible by 17. So this will clearly yield a recurring decimal, won't it? But actually, it's not simplified. 17 over 34 is equal to a half. We know a half clearly has a terminating decimal. It's just 0.5. So why is it that 17 over 34 is terminating when 34 has prime factors other than 2 or 5? It's because it's not simplified. You need to simplify it first, and then you need to look at the denominator. If the denominator has its only prime factors 2 or 5, then you get a terminating decimal. If the denominator has any prime factor other than 2 or 5, you get a recurring decimal. So let's look now at converting the other way. We're going to go from decimals to fractions. So as we saw on the last slide, there are kind of 2 types of recurring decimals. Ones where there are only digits after the decimal place that are recurring, and ones that sort of have a terminating and a recurring part. So the way we're going to convert to the fractions is a little bit different depending on the type of decimal. These ones are really easy. All you do is write the digits in the reptend, write the digits that are being repeated on top, and then the denominator you put with a series of 9s. The number of 9s you use is the number of repeating digits. So here there's only 1 digit that's repeating, so I put 1 9 on the bottom. This is 3 over 9 or a third. But for 0.747 recurring, what we would do is we would write 747, the repeating digits on top. Now, because there are 3 digits in the reptend, we put 3 9s on the bottom. Now, you have to remember when giving a fractional answer, you must make sure your answer's simplified. So 747 over 999 can be simplified because both of these numbers are divisible by 9. You know that because the sum of their digits is a multiple of 9. So dividing top and bottom by 9, we get 83 over 111. So the situation's a little more complicated when you have a terminating and a recurring part. So we're going to use this method here. What we're going to do is let x be the decimal in which we're interested. What we need to do is multiply this decimal so we can isolate the recurring part. I want to multiply this by a power of 10 so the digits after the decimal place are only those that are recurring. So if I multiply x by 10, if I multiply this decimal here by 10, I get 9.6 recurring. So now only the recurring digits after the decimal place. So what I need to do is times it again. I need another number of this form that only has 6s after its decimal point so that I can then subtract. So if I times it by 10 again, I get 100x, then I would have 96.6 recurring. So when we've done that, what we can do is subtract. We can subtract the top from the bottom. 100x minus 10x just gives us 90x. Now 96.6 recurring minus 9.6 recurring, well, these decimals will cancel out. I'll just get 96 minus 9, which is 87. So solving this equation's easy. We've times by 90, we undo that by dividing by 90. So x will be 87 over 90, and then that can be simplified because they're both divisible by 3. It's 29 over 30. All right, let's try this for 0.19 recurring. So again, we let x be this number. We're going to multiply it so there's only recurring digits after the decimal place. So 10x will be 1.9 recurring. 100x will be 19.9 recurring. So now we subtract. We go 100x minus 10x is 90x. But 19.9 recurring minus 1.9 recurring is 18. So this is 18 over 90. And that simplifies to 1 over 5. But hang on a minute, 1 over 5 is equal to 0.2. We've just proved that this recurring decimal is equivalent to this terminating decimal. Sort of a bit of a pathological case. When you have a set of 9s recurring at the end of the number, it's actually equivalent to a terminating decimal. But that's the only case in which it works. So by similar logic, 0.9 recurring and 1 are the same number. All right, let's now have a look at some rational and irrational numbers. So a number is said to be rational if it can be written as a simplified fraction with integer numerators and denominators. So any fraction with integers is rational. 1 over 121, that would be rational. It's a fraction with integer numerator and denominator. Because a number like 4 can be written as 4 over 1, any whole number is rational. So we saw previously that if you have a fraction, you either get a recurring decimal or a terminating decimal. So we can update our definition of rational numbers. Any number with a terminating or recurring decimal is rational. So for example, 0.416 recurring is rational. Why is that? Why are all terminating recurring decimals rational? Because you can write them as fractions. 0.416 recurring is actually just 5 over 12. Similarly, if we have something like 0.28, that's 7 over 25. So any recurring or terminating decimal can be written as a fraction. Any fraction can be written as either a recurring or terminating decimal. So this is what rational numbers are. So what then is irrational? What are the other options besides terminating or recurring decimal? Well, a number can actually have a decimal that is neither terminating nor recurring. Pi is a very famous example of this. Its decimal expansion 3.14159 and so on. It goes on forever, but it's not recurring because there is no pattern. This just keeps going and going, and the digits are seemingly random. Other examples of irrational numbers are when you square root a non-perfect square. So 2 is not a perfect square, so the square root of 2 is irrational. 20 is not a perfect square, so the square root of 20 is irrational. You cannot write any of these numbers as a fraction with an integer numerator or denominator. You cannot write any of these numbers with a terminating decimal or a recurring decimal. So just note, if it's the square root of a perfect square, then it's rational. So for example, square root of 100, that's rational because it just equals 10. If you square root a perfect square, it's rational. If you square root a non-perfect square, it is irrational. So let's now look at operations with rational and irrational numbers. So I've drawn up this table to help you. How you read it is if you perform one of the 4 basic operations with 2 rational numbers, the answer is rational. If you perform one of the 4 basic operations with a rational and an irrational, the answer is almost always irrational. And if you perform one of the 4 basic operations with 2 irrational numbers, the answer is sometimes rational, sometimes irrational. So let's look a bit further at this. So it turns out you can write a rational number as a fraction with integers that have no common factors. So here A and B are just going to be random integers with no common factors. Similarly, C and D are integers with no common factors. So if you go through and add this and you do the algebra, you end up getting AD plus BC over BD. The point is, if A, B, C, and D are integers, AD is an integer, BC is an integer. The sum of these is another integer, BD is an integer. What am I going on about? I'm pointing out that if you add together 2 fractions with integers, the result is another fraction with integers, numerator and denominator. So that's why if you add together 2 rational numbers, you always get a rational answer. It's similar logic for when you multiply or subtract. And if you divide 2 rational numbers, you also get a rational answer as long as you're not dividing by 0. So when you perform operations with 2 rational numbers, you always get a rational number, never irrational. But what about when you're performing operations with rational and irrational numbers? Well, I said it's almost always irrational. So if you have something like pi, you know that pi is irrational. If you add 1 to pi, it's not going to change the fact that the decimal is neither terminating nor recurring. If you times pi by 2, or if you subtract 2 from pi, all of these numbers here will be irrational. So when you have rational numbers operated with irrational numbers, you pretty much always get an irrational answer. There is one exception to that, and that's when you multiply by 0. Because, of course, pi times 0 equals 0, which is irrational. That's a bit pathological. In all other cases, operations between an irrational and rational number yield an irrational answer. So to explain this one, let's just use a couple of examples. If you take root 2 and multiply by root 2, you just get 2. 2 is a rational number. I have multiplied 2 irrational numbers to get a rational answer. But if I were to multiply, say, root 2 and root 3, I get the square root of 6. Now, the square root of 6 is a non-perfect square, so this is irrational. So when you are performing operations with 2 irrational numbers, sometimes you get a rational answer and sometimes you get an irrational answer. So this logic actually leads us to conclude there are actually more irrational than rational numbers. Even though there's infinitely many of these and infinitely many of these, there's more irrational numbers, because you can take any irrational number, add it to any rational number, and the answer is irrational. So you can do pi plus 1, pi plus 2, pi plus 3, they're all irrational. Then you can do root 2 plus 1, root 2 plus 2, root 2 plus 3, they are all irrational. So that's why there are more irrational than rational numbers. All right, let's just take a minute now to look at constructible numbers. So a number k is constructible if it's possible to draw a line segment of length k using only a straight edge and compass. So here we're assuming that we can draw a straight line that has any integer length. So all integers are constructible. So 3 is an example of a constructible number. But because you can use straight edge to divide line segments, to add line segments, subtract them, multiply them, you can get any rational number. So because 3 is constructible, say 3 over 2 would be constructible. Every rational number is constructible, but not every constructible number is rational. Examples of constructible numbers that are not rational, say root 5, the square root of a rational number, the fourth root of an irrational number, so square root of 5 is the fourth root of 5, and any combination of constructible numbers is constructible. So if I add the square root of 5 to the square root of the square root of 5, that will be constructible. Because if I can draw a line segment with this length and one of this length, I can just put them together and get one of that length. So constructible numbers, any rational number, the square root or fourth root of any rational number, and any combination of these. So what are examples of numbers that are not constructible? Well, pi is not constructible. You could easily draw a circle with circumference pi, but you can't draw a line with length pi using just a straight edge and a compass. So all square roots of rational numbers are constructible, but cube roots of non-perfect squares are not. So the cube root of 7, for example, is not constructible. So how would you actually go about constructing these line segments? Well, there's two ways. You can use Pythagoras or the circles. So for the square root of 5, because 5 is 2 squared plus 1 squared, we can draw a right-angled triangle with shorter sides 2 and 1. That's possible using a straight edge or a compass. So if this side's 2 and this side's 1, this length here will be the square root of 5 using Pythagoras. So if we construct these two lines, we can just join up the third line. It will have length root 5. So what about root 6? Well, that's a bit harder because there aren't two square numbers that add to 6 or whose difference is 6. So what we do instead, we can use this trick. What we do is draw a circle. So if I want to draw a line segment of root 6, I start by drawing a circle. Its diameter is going to be 6 plus 1. What you do is go 1 in from the circumference and draw a line segment there. If this is 6 and this is 1, then this segment here will be the square root of 6. So that's why it's possible to construct a line segment whose length is the square root of any rational number. Because you can draw one of, say, length 5 over 8, you can easily draw one whose length is the square root of 5 over 8. And then if you can draw a line segment of length root 6, you could use this trick again and draw a line segment whose length is the square root of root 6. So that's why numbers like these are constructible. All right, thank you so much for tuning into this video. Best of luck studying, but you're a star. You will ace it. This has been the luckiest maths teacher in the world. Have a great day.